Hello, my name is Dr. Gerard Hobley. There are 3 videos covering AS level chemistry energetics. This is part 1. This video is about answering exam questions involving energetics as part of the AQA AS level chemistry specification. However, before we can do this properly, we need to look at some important terms and definitions. You need to be able to write simple balanced chemical equations with state symbols, understand some basic principles and definitions of thermodynamics, do some maths, that is, add and subtract energy change values in order to derive an unknown quantity. Let's take a quick look at the AQA A-level specification on energetics. It says, the enthalpy change of a chemical reaction can be measured accurately. It's important to know this value for chemical reactions that are used as a source of heat energy in applications such as domestic boilers or internal combustion engines. Well, that's not all. Energetics are vitally important in just about every aspect of science. A vital question for a scientist observing any phenomenon is, how is this energetically plausible? The answer may be obvious, or there may be a number of subtle interactions governing whatever is being looked at. Here we will make a start at looking into these interactions in chemical processes. The picture of DNA is here for a reason. It shows a fundamentally important biomolecule which is held together by weak intermolecular interactions. Small changes in temperature can disrupt its cohesion. Understanding energetics is fundamental in such things as gene stability or drug-protein interaction. Indeed, all biomolecular, even all molecular interactions. The importance can't be overstated. A good example of this is in the study of DNA using a technique called UV melting. If I take a solution containing duplex DNA and all the relevant buffers and increase the temperature slowly whilst monitoring the UV spectrum of the solution, the UV absorbance at 260 nanometers will be seen to change over time as a product of the temperature. This can be represented graphically. So here I'm going to put the 2 axes. So here we have increasing temperature. And here we've got the UV absorbance, 260 nanometers. And typically what you would see is as the UV absorbance increases as the temperature rises. However, it does not increase steadily. There's a kind of step in it. So a typical UV melting curve would look like that. And this basically represents a transition between 2 states of the DNA. And we call this the melting temperature. And what's happening is that duplex DNA, so let me draw some duplex DNA. I'll have a purple strand. Breaks down into 2 single strands of DNA. It's essentially an equilibrium system with, at lower temperatures, equilibrium favours the duplex DNA, and at higher temperatures equilibrium favours the single-stranded DNA. And there's a set transition where the DNA essentially melts and the 2 strands break apart. So from this, very detailed thermodynamic data can be derived. If you were to go on to study higher level chemistry, you would be able to see this for yourself. In Hesss level chemistry, energetics is divided into 4 sections. A is enthalpy change. Reactions can be endothermic or exothermic. Enthalpy change, delta H, is the heat energy change measured under conditions of constant pressure. Standard enthalpy change refers to standard conditions, i.e. 100 kilopascals and a stated temperature, for example 298 Kelvin. Students should be able to define standard enthalpy of combustion and define the standard enthalpy of formation. Calorimetry. The heat change Q in a reaction is given by the equation Q mc delta T, where m is the mass of the substance that has a temperature change delta T and a specific heat capacity C. Students should be able to use this equation to calculate molar enthalpy change for a reaction and use this equation in related calculations. Students will not be expected to recall specific heat capacities of substances. There'll be a practical involved in calorimetry, the measurement of an enthalpy change. The next section is the application of Hess's law. Students should be able to use Hess's law to perform calculations, including calculations of enthalpy changes for reactions from enthalpies of combustion from enthalpies of formation. And then finally, bond enthalpies. Mean bond enthalpy. Students should be able to define the term mean bond enthalpy, use mean bond enthalpies to calculate an approximate value for delta H for reactions in the gaseous phase, and explain why values for the mean bond enthalpy calculations differ from those determined using Hess's law. Students should understand that bond enthalpies are mean values across a range of compounds containing that bond. Calorimetry is far better left to a practical session, and I will not try to cover it here. We will look at enthalpy change, Hess's law, and bond enthalpies in these 3 short films. This particular session is about the assumptions, definitions, and conventions, and as such is essential viewing for the rest. The AQA specification states that students could be asked to find delta H for a reaction using Hess's law and calorimetry, then present data in appropriate ways. Examples of reactions could include the thermal decomposition of sodium hydrogen carbonate, the hydration of magnesium sulfate, or the hydration of copper sulfate. To solve the type of energetic problems that you will encounter in your exams, you will invariably be given all the information that you need to do this. All that you will be required to do is organise this information in a way that will allow you to solve a problem. So you will learn some basic definitions and principles, and then how to do the maths. Hess's law is that overall enthalpy change for a chemical conversion is the same irrespective of the specifics of the route taken. Let's be clear at this point. An enthalpy change is a heat energy change measured at constant pressure and usually has the units kilojoules per mole of substance. Hess's law is fundamentally important and is a consequence of the first law of thermodynamics, that is, that energy cannot be created or destroyed. If I had a ball at the top of the hill and rolled it down to the bottom, we can see that there are 2 gravitational potential energy levels, the one from the top and the one from the bottom. The change in potential energy, delta PE, is the change in potential energy of the ball. The symbol delta means a change in something. For example, delta X is the amount of change in X. Try and ignore any horizontal movement in this analogy and concentrate on the vertical movement, i.e. changes in gravitational potential energy. To get the ball back to the top will always require at least the value of delta PE, and probably a lot more. That it will require more energy to get it back to the top is a consequence of entropy, which we'll touch upon in the A-level section of the course. The simple principle is universally applicable. If I could take the ball back to the top using less energy than delta PE, then I would be able to create energy, and as far as any scientist knows, this has never been done. There are no known exceptions to this. If I move the ball up a bit before I let it down, and I'm moving it to a new gravitational potential energy level, and I'm labeling the three changes in gravitational potential energy delta PE1, delta PE2 and delta PE3. Moving the ball up causes an increase in delta PE. If I then drop the ball, the decrease in PE is greater, the overall change is the same, because I need to subtract this value from this value. So overall, this plus this equals this, and we can write this: delta PE1 equals the sum of delta PE2 plus delta PE3. So, how to apply this to chemical reactions? Remember, the overall enthalpy change for a chemical conversion is the same, irrespective of the specifics of the route taken. For a chemical change, in this case an organic compound, an ester being converted into an alcohol, we can draw an energy level diagram. So here's my ester, here's my alcohol. This transformation can be effected directly by reduction with lithium aluminium hydride. Alternatively, the ester could be reduced to the aldehyde with dibal. Don't worry about the reagents at this stage. So I'm converting the ester to the aldehyde, and the aldehyde can be quite easily reduced to the alcohol using sodium borohydride. Overall, delta E, overall energy change, is the same for both routes. There are some important definitions and conventions that you need to know. Delta HF is the standard enthalpy of formation. That is, enthalpy change when 1 mole of substance is formed from its elements in their standard form under standard conditions, i.e. constant pressure, usually 100 kilopascals, and at specified temperature, usually room temperature 25 degrees C or 298 Kelvin. Delta means change in H. H means enthalpy. The Greek letter theta means under standard conditions, and the subscript F is for formation. When we talk about elements in their standard form, we mean that they would occur naturally under standard conditions. For example, oxygen would be O2 gas, or carbon would be solid carbon, or sodium, for example, would be solid sodium metal. An example of a standard enthalpy of formation could be for propane gas, C3H8. It is important that you specify the states of the substances, since phase changes involve a change in energy. For example, water liquid turns to water steam if you add sufficient energy to it. It's still water in both cases. So for propane gas, to HF standard, C3H8 gas, 105. To show this theoretically as a chemical equation, we would write 3C solid plus 4H2 gas goes to C3H8 gas. Please pay attention to the state symbols included in the equation: G for gases, L for liquids, S for solids, and AQ for something in solution in water. Equation is theoretical because if I could burn 3 moles of carbon in 4 moles of hydrogen, I would certainly get a mixture of products and not cleanly 1 mole of propane. Indeed, the vast majority of delta HF standard values are derived from other thermochemical measurements, it being very unlikely that they have been measured directly. Delta HC standard is the standard enthalpy of combustion. These values are likely to have been measured directly in a bomb calorimeter. The enthalpy of combustion is the enthalpy change involved when you take 1 mole substance, burn it in oxygen, or in some extreme cases fluorine under standard conditions, 298 K and 100 kilopascals. As again take propane. Delta HC standard C3H8 gas equals minus 2220 kilojoules per mole, and we would write it as an equation: C3H8 gas plus 5O2 gas goes to 3CO2 gas plus 4 H2O liquid. For a specified reaction, an enthalpy change, delta HR, can be calculated from delta HC standard or delta HF standard values given for the various reactants. Delta HR equals the sum of the delta HF standard for the products minus the sum of delta HF standard for the reactants. The next video in this series looks at examples of using these sums to calculate unknown thermodynamic quantities. So, we've looked at the main principles involved. We've defined Hess's law and what this means. We have looked at some key definitions and conventions, and we have looked at first glance how we can use Hess's law to calculate thermodynamic quantities from other thermochemical data. Next, we will look at actually doing the nuts and bolts of this type of calculation. Please visit our website https://xscience.wordpress.com. There's a link below this film where you can gain access to videos and associated PowerPoint slides, worksheets and answers, tutorials, in-person tutorials for people living in the United Kingdom, other chemical education resources, a range of educational chemistry videos covering topics which students find most challenging. Those things marked with an asterisk, we will post them as we develop them. Thank you very much for your time.